In the last segment, we saw a really simple example of a greedy algorithm. So let's actually push further and see a slightly more complicated example. This is again going to be a scheduling problem. This time, say you're going to schedule events in a seminar room or an auditorium. There are n events, E1, E2, up to En. You have one auditorium available, and you need to schedule as many events as you can. Each event, say event EI, starts at time Si, which is some integer, and finishes at time Fi, which is the finish time, S for start and F for finish. The problem, of course, is that the auditorium can only house one event at a time. So if two events have overlapping durations, then you cannot schedule them both in the auditorium. And we want to find the maximum number of events that we can schedule in the auditorium. The top level question we might ask is, which event to schedule first? What are some greedy choices that we could make? And I want to point out to you that when we say greedy algorithm, it's not always obvious what we should be greedy on. What should we be maximizing or minimizing right at the first step? So we want to decide which event to schedule first. We have a number of different possibilities to try. One possibility might be, let's schedule the event that starts earliest, because we are just wasting the auditorium time until we schedule the first event. So why not try to schedule the event that starts the earliest? Of course, once you decide to schedule that event, you've got to remove all the events that conflict with it, and then go on to recurse on the remaining events. Does this work well? Well, let's look at this. Here is an example. You see the event in red is the one that starts earliest. It starts earlier than all the other events. But if you decide to schedule it first, all the other events conflict with it, because this event is lasting for the entire duration, if you like. And so you will only be able to schedule this one event and none of the other events. So that was not so good. We could actually do better. So that policy, that greedy policy of scheduling the earliest starting event first, is not a good algorithm. Let's try to examine another greedy policy. It might be to schedule the event that lasts the shortest duration first. And of course, every time you decide to schedule an event, you should remove all the events that conflict with it. Why might this be a good idea? That the thinking is, well, if you schedule short events, they don't hold up the auditorium for too long, and it will be available for other events. That seems reasonable on the surface again. So let's look at how that would work. Here is an example. This example shows you the red event is the shortest event. If you do schedule it, you forego the possibility of scheduling the other two events, which both conflict with the red event. On the other hand, if you didn't schedule the red event, then you could schedule two events in its place. And therefore, scheduling the shortest event first is not a good idea either. So neither of these greedy approaches works well. So let's ask ourselves what other greedy idea might work. Again, the main point I want to make with this example is that just because you think you're going to use a greedy algorithm, it's not immediately clear what parameter you should choose to be greedy on. So the idea that works is to sort the events not by their start time, but by their finish time. So let's actually imagine that we've sorted all the events by finish time. So the earliest finishing event is number 1, the second finishing event is number 2, and the latest finishing event is number n. So that I'm going to now call the events E1, E2, up to En in this order. So I've just relabeled the events. So again, that the earliest finishing event is E1. Okay. And the greedy algorithm says the first job I schedule will be E1, basically the earliest finishing event. And once I've put that in on the calendar for the auditorium, I remove all the events that conflict with it, that overlap with it. I have a remaining set of events I need to schedule. I do the exact same thing. I recurse in the exact same way, meaning out of the remaining events, I schedule the one that finishes first, remove the events that conflict, and so on and so forth. So the question is, does this produce the optimum solution? Could there be an optimum algorithm, not this greedy algorithm, that schedules more events? So here is an example. The red events are the ones that are chosen by the greedy algorithm. You can see that the first red interval here, shown here, is the one that finishes first. It finishes here before anything else. So it's the event that will be scheduled first. Once that's scheduled, we've got to knock out all the events that overlap, which means this one is out and this one is out. And now you look at the remaining events and ask which one finishes first, and it'll be the second red one here. And once that's chosen, you've got to knock out the ones that overlap, which are this one and this one. And now what's the best event to schedule is the third one here. And once that's scheduled, you've got to knock out anything that overlaps. At the moment, there are no others. So then you got to schedule the next event, which is this fourth one. And when you do, you knock out this one because it overlaps, and you knock out this one because it overlaps. And finally, you schedule the fifth one. So that's the greedy algorithm. Now, we can ask ourselves, could an optimum algorithm have produced more events, scheduled more events in the auditorium? So the intuition for this greedy algorithm is that choosing the event that finishes first leaves the most time available for the remaining events. But can we make that into a more solid proof of correctness? So the optimum couldn't do better. Let's prove that the first choice that the greedy algorithm makes can be continued on to an optimal solution. This is called the greedy choice property. Whenever we design a greedy algorithm, we have to prove something called the greedy choice property. What is the nature of that property? It just says the first decision made by the greedy algorithm can be continued on to a series of decisions that overall leads to an optimum solution. So how do we prove the greedy choice property? So that's one thing. And then the other thing we have to prove is that after you make the greedy choice, you get a new subproblem. In this case, after you choose one event, you eliminate the conflicting events and you get a new subproblem that way. And you should solve the resulting subproblem also optimally. This is the optimal substructure property that's needed both for greedy algorithms and for dynamic programming, meaning within the optimal solution to the whole problem are buried optimal solutions to subproblems. So let's prove the greedy choice property for this activity scheduling problem or event scheduling problem. So suppose the optimum doesn't necessarily choose the event E1 that finishes first, but instead it makes a series of choices E sub O1, E sub O2, E sub OK. So these are just some events out of the sequence of n events that we are given. E sub O1 might be like E17 or something like that. So it's some event out of that sequence. And say these are the events also ordered in increasing order of finish time. So E01 is the one that finishes first among the events that the optimum chooses. The typical way to prove that greedy choice holds is something called the exchange property. What we argue is that if the optimum's first choice, E01, was not equal to E1, then we can we can throw away E01 from the optimum solution and add in E1 to the optimum solution and still get an optimum solution. This shows that, in fact, you didn't have to choose E01. You could have chosen E1 and continued on to an optimal solution. So the picture looks a little bit like this. The optimum chose E01. Here's E01. It ends somewhere. What do we know about E1? E1 was the earliest finishing event. That means it must have finished earlier than E01. So E1 finishes somewhere here. E1 is something like this. And what do we know about E02, E03, and the rest that the optimum chose? Well, because the optimum was able to choose E01, E02, all of those things, you know that none of them conflict with each other. So E02 must actually begin after E01 finishes. And E03 must begin after E02 finishes, and so on. So that's the picture for the optimum. And it's clear that we could have dropped E01 from the optimum solution and added E1 to the optimum solution, and we would still be a consistent solution. There are no overlaps because E1 finished before E01. So this is the proof by exchange property that the choice of picking E1 as the first event is completely fine. Whatever optimum solution you find, you can make sure to put E1 in there and it'll still be an optimum solution. It does not have any overlap with the entire interval from the start of event O2 to the finish of interval OK, of event OK. So that's proving that the greedy choice property holds. The other property we want to have hold is the optimal substructure property. So how does that work? So suppose you consider the optimum solution E01, E02, EOK. Again, these are some set of events that the optimum chooses. The claim is, if you look again at E01, I'll draw that again, E01 is here, and look at everything that starts after E01 finishes. This is F01, the finish time of O1, and this is the start time of O1. So you look at all the events that start beyond here. Okay, so recall that once you've chosen E01, you've got to eliminate every event that overlaps with it. And of course, E01 was the earliest finishing event in the optimum, so we've got to look only on this side. What the optimal substructure property says is that for this subproblem that lies to the right of F01, we must choose an optimal sequence of events. We shouldn't choose anything less than the optimum. And that's pretty clear, because why would you choose something less than optimum for the remaining subproblem here? Because if you chose something less than optimum, you could replace it with a solution that actually chooses an optimum subset of events. And so the optimal substructure property also holds, and therefore this greedy algorithm is correct.